Good morning. And this lecture, what we are going to look at is some graph algorithms in streaming model. Okay. So you've been looking at streaming. Um, there are some input elements, packets coming, and you need to compute something, right? Number of distinct elements, or number of elements, or do some sampling. And the space was a big criteria, and you're doing it in small space. In particular, ideally polylog space, right? Log n or log n or polylog. That was the kind of things you've seen. So today our object is going to be a graph, and the vertices, let's say it has n vertices. Everybody knows, my algorithm knows, and it's told in advance. And then edges are coming in the stream. Okay, so that's the model we're going to have. There are n vertices, n is known, and edges are coming. And as and when edges come in this graph, I have to solve some questions, some natural graph questions. Okay. One by one. So when the new, so there some, we are trying to solve some problem. Let's say you want to find the shortest path between a pair of vertices or something. That's a query you want to answer. When a new edge comes, you update your graph, and then you should answer the question. Okay, and the time is take to answer the question is a secondary thing. We are, in fact, you can worry about it, but in this lecture we are not going to worry so much about it. We are going to worry only about the space. Okay, how much space you are going to use to store your graph or whatever, some subgraph or whatever information you need to answer the question. You're going to store that, and you want to talk about the space to store that graph. Okay. Now, how do we represent a graph? Adjacency matrix or adjacency list, right? So these are two standard ways to represent a graph. How much space does it take? Okay. So suppose number of edges is m, right? This is a changing thing, because as the edges come, your m is going to increase. Adjacency matrix takes how much space? N square bits, and adjacency list will be m plus n in the order of that many cells. Now each cell is some sort of a pointer or an address in the range 1 to n, so I will add some log n bits for it. So it's, I'm going to say it's something like m plus n Now, since I said that time to compute your solve your problem is not going to be important, one possible way is to just store the whole graph, right? Whenever new edge comes, update it, store your graph, and whatever time it takes to solve your problem, answer that. Okay. Now that space is going to be like either n square or m plus n log n, and our goal in this is to do it with preferably much less space. Okay, so I want to do much less than n square or much less than m log n bits. Okay, and it turns out most of these problems are hard. That there are very few problems where you can do anything substantially better than m log n bits. And tomorrow, next week, Deepak will have a session on lower bounds for these space in graph streaming, where you will say that there are a few problems you cannot do in less than so much space. Okay, so but there are a few problems where you can do slightly better than m log n bits, and that's the kind of 2-3 problems we are going to look at today. Okay, so goal again, unlike the kind of algorithms you have seen where we were trying to do it in polylog space, right? Here, even something like n log n bits is good for us because that's the best you can do. Okay, we are just trying to beat n square or trying to beat m log n. So, we will have schemes where the space used will be like n log n, and it will be complemented by some lower bound next week. So, we are deviating from this polylog requirement, and here we are talking about sub-quadratic. Okay, we are just going to settle for something like that. That's all. Okay, so let's get started with problems. So, the problem 1 I want to talk about is this Boolean question: is G connected? Okay, so now without the streaming constraint, in the classical world, if I give you a graph, how do you check whether the graph is connected? Yeah, connected means what? There must be a path between every pair of vertices. So, how do you check? Hmm? Hmm. Okay, that will only tell you about a pair of these vertices. I want a path between every pair of vertices. Hmm. How do you check that? Okay, so I forgot to say we are working in undirected graphs. Okay, of course we can also talk about directed graphs, but today we are going to be talking only about undirected graph. Yeah. BFS, right? BFS, DFS are precisely graph exploration techniques to check whether check for paths. So you just start at a vertex, grow a BFS, and at the end of it, if you can reach every vertex, you know that graph is connected, otherwise it's not. Okay, fundamental algorithmic question, and that's what you can just do a BFS and check. Okay, so that's without worrying about streaming. And how much time does that take? BFS, B plus E, so or M plus N. If there are M edges and N vertices, in linear time, you can check whether the graph is connected using BFS or DFS. Okay, so now, but now we have to sort of switch gear, and we are looking at a slightly different model. We have to maintain something so that when a new edge comes, we will be able to answer whether this current graph is connected. So, how do we maintain? What do we maintain? That's the question, right? And because the space is a constraint for us, so what do we maintain so that, and what sort of update you will do when the question, when an edge comes to answer this question? So, I have a current graph, some snapshot of the graph I want to maintain, because I can't store the whole graph, that's going to take me a lot of space. So, some snapshot I will store, some fingerprint, something, and when the new edge comes, I will do some query on this and answer whether the graph is connected. So, I want store enough to be able to answer this question. store a pair of vertices that are not connected. So there may be several pairs, right? Okay.
An incoming edge is kind of connecting with any of the pairs.
Okay. So one idea what she's saying is store all the pairs between which there is no path. But that's like could be as bad as n choose 2, right? Incidence matrix.
We can make it as
Okay.
create the what is it is connected to the path. Let's say at the moment of T, we have a section, some vertices are not connected.
So okay, let me ask this question. So maybe the graph is not connected at this point, but when that new edge comes, the graph becomes connected. Then what is that new edge doing? Yeah, I'm a little better. Yeah, sort of creating a path. Yes, but so at this point the graph is not connected. So I have at least two components, and when the new edge comes, the graph becomes connected. So what is the edge doing? The edge is doing something. What is it doing? It's connecting these two components, right? So let's say I have maintained the graph is not connected, so I maintain two components. And what do I maintain? I maintain the set of vertices in each of these components. Okay. You said every pair of vertices which are not connected, some thing like that is what I'm going to store, but but I there are some pair of vertices which are connected. So somehow there is some sort of an equivalence class of all these vertices that are in one component. Here is a set of vertices that are in another component, and I store these equivalence classes or store these sets. And then when an edge comes, what do I check? Whether the endpoints are whether the endpoints are in the same component or a different component. If it's the same component, that's not useful to me. I just throw it away. If it's connecting two components, I'll add that edge and then update my structure. So what I'm going to store, so the solution store a spanning forest. Okay. So what that means is that here is a set of vertices which are connected. Here is another set of vertices which are connected. Here is another set of vertices which are, and so on. So this is what I store. Okay. What do I not store? I mean, why is this a subgraph of the graph? Because there may be edges in the same component forming cycles which I don't store because I don't need to. Okay. So all I am going to store is essentially sets of vertices in each connected component. That's my data structure, if you like. Okay, that's my data structure or what I'm going to store. And now the algorithm is so with edge E comes if E equal to UV and U and V are in different components. Okay, so I maintain a set of edges, let's say F. Okay, which is initialized to empty set. I start with nothing. Then that's all. So what am I storing? I'm storing a set of edges in a spanning forest of the graph. Okay, And when a new edge comes, I check whether the endpoints are in different components. If so, I will add it to my collection of edges. Otherwise, I just discard it. Okay, that's my algorithm. Well, I have to answer whether the graph is connected or not. When is the graph connected? Number of components is 1. How do I even figure that out from what I store? U and V. Yeah, but so there is no finally, it goes on forever. Okay, so at some point there is the edge comes, I update my structure, and now I have to tell the user is waiting. I have to say whether the graph is connected or not. Okay, so he's right. If the number of components is 1, I know the graph is connected, but I'm not storing enough information to say. All I am storing is a set of edges. So when is, yeah, all the vertices are in the same component. Yes. Cardinality of f equal to, it should be n, or what is it? That's the correct direction. N minus 1, right? So if cardinality of f is equal to n minus 1, then return yes. Why is that? What is the graph theoretic property you are using? Not minimum spanning tree, any tree. Any tree on n vertices, has n minus 1 edges, right? Because there are n vertices and I am storing this forest. As long as it's a forest, it's going to, I mean, it has more than one component, the number of edges will be less than n minus 1. The moment I have one component, because I am always storing a tree, the number of edges will be n minus 1. So, let me just put this lemma, which could be discussed in the tutorial again if you have not seen it. Any tree on n vertices has n minus 1 edges. What is a tree? Acyclic and connected acyclic graph, right? If it's not connected, it's a forest. So a connected acyclic graph is a tree. That's the definition of a tree for us. Prove that any tree on n vertices is n minus 1 edges. Okay. If you have not seen it, it's an interesting, it's a very basic theorem in graph theory, and if there is time, you can look at it in the tutorial. Okay. Okay, so my structure basically stores a collection of edges of a forest, and so all I'm saying is you don't need the whole graphs. In particular, for each component, I just need a spanning tree. I don't need the edges not in the tree in this component. I don't have to remember them, because for the purpose of answering this connectivity query, all I care is this set of edges. I don't need the other edges. So that's the saving I do. Okay. So how much space do I use? Because I said space is the important thing. That's what we care about. Because f stores some edges. That's my only storage. Okay. And each edge is basically 2 endpoints, and each endpoint is a number between 1 and n. So it takes about log n bits, and I store at most n minus 1 edges, because the moment I have n minus 1 edges, I know there is one component. I can keep on saying that the graph is connected for any other edge that comes. Okay. So the space is questions? Okay. Now you can talk about what in the stream I am asked to delete edges. Okay. This thing doesn't work anymore because I'm not storing enough, because if I store Let's say in one component I stored some tree, and the algorithm is asking me to delete these two edges. I am not sure that this component is broken. Why not? Because I did not store some edges, remember. So there are other edges which I did not store. They may be connecting these two pieces, right? Because there may be an edge like this in the graph which I did not store it. So if I want to do deletion, the whole it's a lot more complicated problem, and that's for another lecture or more research direction, I would say. Okay, so you're only talking about insertion only tree. So you have to, it's a really interesting problem, very complicated. It had a long history of some 10 papers written on that. If I also allow deletion, how much space, what structure do I use, and so on. Okay, so let me make a note. We're doing only insertion. So in the data structures course, maybe you will actually look at how, how much time it takes. Like I said, we don't worry about time here, but you can ask, how quickly can I check whether the two endpoints are in different components or not. Okay, so people have seen an advanced data structures course who would recall that this is the set union, this find union find problem, right? You want to maintain a collection of sets such that you want to know what, given an element, what set it belongs to, and given a pair of sets, I want to merge them. I want to do a union of these two sets. Okay, how efficiently can I do? There are very interesting data structures for that, but we won't bother about it because, as I said, time for doing this is not our current concern now. Okay. Okay, that's the end of connectivity question. Any question? Then I move on to a different problem now. Okay. Let's say I want to check whether the graph is bipartite. Okay. So what is a bipartite graph? No edge is in the same set. Right? There is a way to partition the. How many people have heard of this bipartite graphs? Okay. So you can partition the vertex set into two parts such that there are no edges within each part. Okay. This bipartite graphs come up in real world applications many times because you're talking about men and women or machines and jobs and resumes jobs. There are all kinds of problems where your graph has a natural two parts where each part has no edge. Okay. So now here is this question, and it's also known as two colorable, right? I.e., we can color the vertices of the graph such that whenever there is an edge, the endpoints get different colors. Okay, so if it's bipartite, you can color one part as one color, another part as other color, and since all the edges are going across, the endpoints of every edge gets different color. Any characterization for bipartite graphs? Yeah, what is that? What? It should be a odd length. The connection to odd cycle is correct, but so what? A graph is bipartite if and only if number of edges in a cycle. So, let us look at an odd cycle. And let us see whether I can properly two color this, right. Suppose I give color 1 to this vertex necessarily gets color 2, this should get color 1, this should get color 2, and I am stuck here. I can't color 1 or 2 because it has neighbors in both sides. Okay. So, an odd cycle is clearly not bipartite, and it turns out that a graph is bipartite if and only if there is no odd cycle. So, if there is an odd cycle, you have a problem. Here is a proof, and it turns out the converse is also true. If there is no odd cycle, then you can happily partition the vertex set into 2 and make it 2 colorable. Okay. So, this is again another interesting. Okay. So, graph theorists will see a lot of interesting exercises here. Okay. So, so okay, so let us again go back to our classical world, no streaming, nothing. Given a graph, how do I check whether the graph is bipartite? Okay, so you've seen it or not? Some of the third year undergrad Shastra guys. Have you not seen it in your algorithms course, graph algorithms or graph theory, discrete math? So, how do you check whether a graph is bipartite? Well, sort of you can do a BFS, start from a vertex, color it 1, color all its neighbors 2, and the neighbors 1, neighbors 2, and so on and so forth. Okay, so basically grow a BFS starting at a vertex, and whenever there is an edge where both endpoints are in the same level, then it turns out you can extract out an odd cycle out of it, and otherwise this coloring is nice and proper to coloring. Okay. So, you can again just with BFS and little more checking in order m plus n time, you can check in order m plus n time. Okay, now let us come back to our streaming problem. Edges are coming. What do I store so that when a new edge comes, I can figure out whether or not it is bipartite. Okay. So, let us come back to this sort of solution we had for connectivity. So, again time is not such an issue for us as I told. So, suppose I maintain this spanning forest, let us say, and then when an edge comes, if it connects 2 components, I will add it, no problem. But if it connects, if the endpoints are in the same component, I can't just discard it, I need to do something, right. What do I need to do? Check whether in that component there is an, whether it forms an odd cycle, that is all. That is all, there is nothing really much more than what we are doing here. I will say and maybe argue why that is enough. So, solution again here is store a spanning forest. So, start with the edges currently in the spanning forest, and when the edge E comes, check if F, well, if E joins two components, then F is F union E, because no problem, it is connecting two components, so it's not going to even form a cycle. Forget about even forming an odd cycle. So I will add it to my collection, and so now I have again a spanning forest of the original graph. But if E joins if the endpoints of are in the same component, then I have a check now. If F union E as an odd cycle, return no, else return yes. In either case, I am not adding the edge E. So always I maintain the spanning forest. So when the new edge comes, if it connects two components, I will add it. If it connects, if the endpoints are in the same component, then I know that it is not adding anything more to the connectivity, because the component it's already in the component, but it may create an odd cycle, which I will check. You know, how do you check? Well, how fast can you check is an interesting question, but I'm not going to worry about time. So you can do whatever the algorithm I said, do a BFS and check. And if it forms an odd cycle, then you report that it's not bipartite, otherwise it is bipartite, and either way I discard that edge. And the claim is that this is good enough, that if the algorithm returns it is bipartite, then it is bipartite, even though it is not storing all the edges of the graph. Okay, because the external other edges can only form an even cycle with whatever you have stored, and so the graph will be bipartite. So the space again is like before. So let me again remark here, how fast can you do it? It's an interesting secondary question. There is another algorithm for checking bipartiteness. I will mention that. Again, it's based on a black box graph theory theorem, nice theorem, I would mention it. So another structure, another algorithm. So given G, let G prime, I'm going to construct so V prime has two copies for every vertex. For all V in V, and E prime equal to U1 V2 comma V1 U2 for all UV in E. Okay, so let me draw an example. Here is my graph G. So my G prime has two copies of the same vertex set, and whenever there is an edge U comma V, this U1 will be adjacent to V2 and this V1 will be adjacent to U2. So this is my G prime. Okay, is there a name for this graph? Product something. So for example, if G is like this, then I will have A1, A2, B1, B2, C1, C2, D1, D2. Every vertex is copied. And since there is an AB edge, it will have A1, B2 and B1, A2. AD edge will be like BC edge will be, and CD edge will be like this. And here is the interesting claim, left as an exercise, maybe can be done in tutorial. G is bipartite if and only if G prime is not connected. Okay, so somehow when you have this bipartition, you the graph, the G prime, becomes disconnected, and if it's if it's not bipartite, then this G prime will be connected. Okay, so now in my streaming world, can I use this claim to check for bipartition, whether a graph is bipartite? Right. So I have this current graph, edges are coming, and I need to check whether this new graph is bipartite. Okay, that's the goal. I gave you an algorithm which is to do something, but I am giving can you think of a different algorithm where the edges are coming using this claim? Well, I can construct G prime and use my connectivity solution, right. My problem 1 was checking whether a graph is connected, remember, and so all you do is whenever an edge comes, it will correspond to 2 edges in G prime. So maintain this thing and maintain the spanning forest of G prime, okay, and do the connectivity solution. Okay, people seem to be lost. Good question. How much? What happens to the space? Yes, very good question. So how many vertices are? If G has n vertices and m edges, how many vertices are there in G prime? 2 n vertices and 2 m edges. That's all. So it increases by just doubles it. Asymptotically, it's not such a big thing. Okay. So I mean, the reason I want to say is this. Checking for bipartition was a little non-trivial, but this theorem tells you, okay, use the connectivity solution and on G prime and check whether G is bipartite or not. Okay, so this, I mean, tomorrow you're going to, or next week, you're going to see these reductions, NP complete reductions, something similar where use the solution for one problem to solve some other problem. Okay, that's always useful. Why reinvent the wheel? If you can prove some theorem like this, then use the connectivity solution to do this. Okay, so the third problem I am going to talk about given x, y, give me the distance between x and y, right. It is an undirected, unweighted graph. So, distance between x and y is the length of the shortest path between x and y. So, again remember that the whole theme in this whole thing is that I do not want to remember the whole graph, I want to remember some snapshot, some picture, some fingerprint of the graph because space is limited, but still I want to be able to answer this question. Okay, and what we said in the case of connectivity or the bipartiteness is that a spanning forest which is really sparse because each component has only some n minus, or if there are n1 vertices, there are only n1 minus 1 edges. So, in order n log n bits, you can remember enough to be able to correctly answer whether a graph is bipartite or whether it is connected. Okay. But this problem, so again I forgot to say, given your g and xy. Now think about this problem. Even if I store one edge less, because x and y are arbitrary, the query is going to come for arbitrary x and y and ask me whether there is a path between x and y, right. So even if I don't, if I remove one edge of the original graph and store a smaller subgraph, I may not be able to answer this. So in particular, you don't know what x and y is, and suppose there is, you've removed an edge of the shortest path between x and y, then maybe the new shortest path will not be exactly the shortest path between x and y. There is a unique shortest path. Okay, so you can show, which you will see when we talk about lower bounds, that pretty much if I have to answer this question exactly, you have to remember the whole graph. So I'm going to now relax and say, okay, I don't want it exactly, give me some approximate distance. Okay. So the goal now is not necessarily to find some d hat xy, which is at most some t times dxy. Okay, t is some parameter. So what I am going to store is a subgraph because I am limited by space, and because of that I may not be able to answer your shortest path question exactly, but I will store enough so that the shortest path length in this subgraph is not too bad. Okay, it's at most t times. So t is a parameter which we will fine tune as we go along. Okay, so that's the solution we are aiming for. Okay, so let me just say, because computing exact dxy requires, so this is a technical statement, I am not going to prove it, storing the whole graph. So here is the solution. Okay. Again, I am going to store a set of edges. So basically a subgraph of the graph. And starting with empty set. Now when an edge comes, I need to know, should I include it in my graph or not, right. So this, and what is the criteria by which I am going to store. So I am storing a set of edges. So let us say H is that subgraph. H has the entire vertex set and F this subset of edges. So if distance between x and y in H is less than if it's greater than t, then I am going to add it. otherwise discard it. That's all, right? So I'm at any point of time I'm storing a subgraph. So the entire vertex set and some subset of edges, let's call them F. Now when a new edge comes, I will check the distance between these 2 points in this subgraph. If it is more than t, then I'm going to say this edge is useful, so I'm going to add it. Otherwise, I will discard it. Okay, that's my subgraph. That's all. That's my solution, which stores how much. Okay, how much space? We'll come to that. So the claim is the distance between x and y in h, I am storing h is at most t times its original distance in graph. Okay, so this subgraph is a good enough approximate, and it has enough to find an approximation to the shortest path. Okay, so this is not very hard to show. Okay, so let's try and prove it. Okay, so suppose x to v1, v2, some vk, y be the shortest path between x and y and g. By the way, this is also called a T spanner. Okay, you might see this word. So in the original graph, suppose this is the shortest path between x and y. Will the same path be existing in H? May or may not. If it exists, good. I already have the shortest path in H. Suppose some edge of this is missing in H. Why was it missing? Okay, so suppose some vi plus 1 edge is not in H. Why? Right. So I have this path v1 or x to v1 to v2, v3 up to vk. This is the shortest path in G, and maybe this some edge is missing in H. Why was this edge missing? There may be path between. No, let's go back to our algorithm. Why did we not include an edge? No, let's just go back. Why did we not include that edge xy? Because the distance, current distance between x and y is less than or equal to t. That's why I did not include. Okay. Later on, I added some more edges. The distance might have even become smaller for all you know, but I know that this vi plus 1, this edge may be missing, but there is a path of length at most t in H between these 2 points. So, for every edge which may not be in H, there is a path of length at most t sitting there in H. Okay, so that's the end of the argument. So, your path of length k may be blown up by at most t times k in H. That's all, because that's the reason we did not include that edge is because there is already a short path. Short means at most length t. Right? If such a path exists. Okay, so I am going to just say hence distance between x and y in H is at most t times distance between x and y in G. So, if you are willing to settle for an approximation factor of t, I do not have to remember G, I can throw away some edges and I store H. But how much saving did I do, right? What is H? Yeah. At this point, the entire argument is whatever at this point. I have an edge coming and at this point I have to tell what is the shortest path, right. So, this whole argument is that there is an edge E coming and I do it, and in my current graph, whatever is the current shortest path and what is the shortest path in H. Okay, how much space have I stored? What is the space? Well, I stored this subgraph H, whatever the number of edges in F is a subset of edges I have stored and whatever that space is. Now, what is cardinality of F? We will resort to another nice theorem in graph theory, which will be again picked up in tutorial. Now, what is the, okay, so before I mention the theorem, let us look at some property of H. What can you say about the length of the shortest cycle in H? This is also called girth. In girth, in H, for example, can I have a cycle of length less than t? Okay, so let us go back again. So, I want to be able to answer the distance queries. So, my idea is that, okay, I mean, I can't answer exactly, give me some parameter, I'll answer up to that approximation ratio t. And what is the algorithm? Whenever there is an edge, if there is already a path of length at most t in the graph between these two endpoints, I discard it, otherwise I add it. That is my algorithm to store what is the subset of edges I add. And I now want to argue that the subset of edges I have stored is reasonably small, the number is small. Okay. To argue that, I want to just capture the property of H. What is the property of H? What can you say? Can H have a cycle of length at most t? Why not? Because I asked the way I asked, the answer must be no, right?
Between two vertices, if there is a smallest, we take that, not the other.
Exactly.
So it is not possible to having cycle between any two.
Of length at most t, right? Because, or even t plus 1. If H has a cycle of length less than or equal to t plus 1, let us look at this cycle, right. And let's look at the last edge added in H in this cycle. So, maybe this was the edge which was added, some E. But notice that there is a path between x and y of length at most t, the remaining edges of the cycle. In that case, I will not have added E. That is my algorithm, right? Because if there is a cycle of, if there is a path between x and y of length at most t, do not add that edge. So, we will not have added that edge. Okay, so that is a contradiction. No, I am going to just say there is a contradiction. So, girth of this graph is strictly more than t plus 1. Now, there is a theorem, interesting theorem in graph theory, which will be left as an exercise. Any graph on n vertices and girth more than t has at most 2 minus 2 by t. Okay, so I'm going to something like this. I'm not exactly sure. This can be looked at in the tutorial today or on Monday. So, it is a pure graph theory question, right. So, any graph, all I am saying is its girth is large, then it cannot have too many edges, because this, you know, if you have a cycle, the short cycle, then the cross edges are not present, because that they will give me a shorter cycle. So, somehow you can argue that it has at most so many edges. So, if I want, for example, a 3 approximation to these distances, t is 3, then this is like, you know, n to the 3 halves edges. Okay. So, something better than n square, that is all we are saying. Some really sub-quadratic space is what I am going to use to store a h. Okay. So, in summary, if I want exact distances, I can't do better than just storing the whole graph. I haven't proved it, maybe it will be proved on Monday. And so, I am going to settle for approximation, and there is a trade off between the approximation ratio and the space I use. If I really want very good approximation, maybe I will use more space. If I am willing to settle for a little more approximation, I have low space. Okay. So, this is another interesting trade off between space and approximation. Again, you would have seen it in other contexts in the streaming algorithms. Okay. So, last example, last problem. Maybe find the maximum matching in the graph. Right. So, you all know what a matching in a graph is. It is a collection of disjoint edges, and there are very classical algorithms for finding a maximum matching in any graph. If it is a bipartite graph, you can use the max flow technique to find the maximum matching. If it is a non-bipartite graph, there is a very classical Edmonds algorithm to find the maximum matching in a graph. Okay. So, now in the streaming model, what I am asking for is that a new edge comes, what is the maximum matching? What do you store so that you can answer this maximum matching efficiently? Again, it turns out it is one of those where it is very hard to answer exactly without storing the whole graph or something in sublinear space or subquadratic space. So, we are going to settle for approximation. So, on the other hand, 2 approximation is fairly trivial. Okay. So, what is the 2 approximation? Solution, simply maintain a maximal matching. Okay. Do you know the difference between maximal and maximum? In general, it is a generic concept. What is the maximal set and maximum set? Anybody knows? Okay, so maximum refers to the largest cardinality, but maximal says that I can't add any more. Okay, it may or may not be of the maximum size, but it's just that I have a current solution, I cannot add anything more to it. Okay, so let's see an example. So what is the maximum matching in this graph? A, B and C, D, right? So maximum matching is of size but suppose I picked up the edge BC in the matching. Okay, can I add any more? No, and it is a maximal matching. Okay, it is not of the maximum size, but it is maximal because I can't extend it. Okay, that's the difference between maximal and maximum. Okay, now anything maximal is in general relatively easy to do because you can just sort of do some greedy approach. You know, I just go and collect something, and you know I can't, if I can extend it, otherwise don't you can't, and it's a maximal matching. Okay, so anything maximal is easy. So do you see that in the streaming world, if I want to maintain a maximal matching, okay, it's fairly easy, right? I have a maximal, so let's say I maintain a maximal matching, an edge is coming. What action should I do? Okay. Exactly. Otherwise, just add it, right? If that endpoints of the edge, because an edge is coming and the edge may have intersection with the vertex in this graph. If it's completely disjoint from all the edges I have collected, I will add it to my matching. It's another maximal matching. If it intersects one of the vertices in the maximal matching, do not add it. Okay, it's a fairly simple, trivial thing to do when a new edge comes, and I maintain this maximal matching. Okay, so so algorithm, when E arrives, if E can be added to the current maximal matching, add it. Else discard it. Okay, E can be added. What does that mean? That an X and Y are not an endpoint of my current matching. Okay, and this, how much space will it be? Because I am just storing a matching. Okay, if there are n vertices, how many edges can there be in the matching? N by 2 or something. Okay, and each matching has 2 endpoints, each one takes n log n bits, so it's some order n log n bits. Okay, fine. I mean, I really wanted maximum matching and you created a maximal matching. What is the connection? Right? The claim is that maximum matching is at most 2 times maximal matching. So, what I am storing is sort of a 2 approximate solution, right. The maximum matching is 100, I may be storing some 50, not less than that, 50 or above. Okay. So, I am not too far from the optimum. Why is this true? Let's, there's a very simple proof of it. There are many proofs you can verify this. So, here is my proof. So, there is a notion called vertex cover. How many people have seen this notion of vertex cover? Okay. What is vertex cover? Yeah, go ahead.
So it is a subset of vertices which cover all the vertices of the entire graph.
Cover all the,
Vertices of the entire graph.
not all the vertices of the graph, all the edges of the graph. It's a set of vertices that cover all edges. So, that means pick any edge, at least one endpoint must be in this subset. That is a vertex cover. Okay. One can show that minimum vertex cover is at most 2 times maximal matching. Why? Because if you take the set of vertices and maximal matching, they will cover all the edges. Is that clear? Right? So, this is my maximal matching. There are a lot of other vertices here, sure. There are more vertices here, lots of edges here and things like that. So, all I am saying is this set of vertices cover all the edges. Why? Cover meaning if you take any edge, at least one endpoint must be incident on this set. Exactly. If there is an edge which is not covered by it, why did you not add it to your maximal matching? It contradicts the fact that this is a maximal matching. Since this is a maximal matching, there is no edge exclusively outside. So, every edge will have some endpoint. So, if you take all this set of vertices that form a vertex cover. So, minimum vertex cover size, I mean, because this is one vertex cover, 2 times the number of edges in the maximal matching. So, the minimum vertex cover may be even smaller than this. Okay, that's the reason for this, because the set of vertices in a maximal matching, because that's 2 times the number of edges, is a vertex cover. So, the minimum vertex cover may be a different vertex cover, but this is certainly a vertex cover, minimum vertex cover size may be smaller. And this is also not very hard to see that the maximum matching size minimum vertex cover must be at least the size of the maximum matching. These are all some standard graph theoretic things, not very hard to prove. Why is this? Because if you take maximum any matching for that matter, each matching edge requires one vertex to be covered in the in the vertex cover. These are all disjoint. So, one vertex cannot cover multiple edges. So, for each edge in the matching you need at least one vertex. So, minimum vertex cover, any vertex cover should have size at least the size of the maximum matching. So, together you have maximum matching is at most 2 times maximal matching. So, in n log n bits in the streaming world, I store only a maximal matching and it is already a 2 approximation for maximum matching. Okay, good. I think I have reached my time. So, that is all I am going to say. Let me summarize what we did. We were looking at streaming model where edges are coming in and we need to answer some query about the current graph, and we care about the space we use. Almost always n square is sort of a lower bound, which we will see next week. But for certain problems, for example, we check connectivity, whether a graph is connected can be checked using n log n bits of space. Whether a graph is bipartite can be checked in n log n bits of space. And when it comes to approximation, we can do a t approximation of the distances in some subquadratic space and 2 approximation for maximum matching in subquadratic space. Okay. So, this is the game in graph algorithms and streaming model. Now, we said we are going to do only one pass. Now, you can also ask this question, okay, I do not want to necessarily, moment the edge comes, I do not necessarily need to answer it. I store some information, come back and answer it, okay. Turns out it does not really make too much difference, but that is another set of models in which graph algorithms are studied. And there are very interesting lower bounds which are not very hard to show, to say how much any one pass streaming algorithm must use at least so much space. Okay, so that kind of reasonably accessible lower bounds, which we will see next week by Deepak Rajendra Prasad will give you some lower bound lecture. Okay, we'll stop. Thank you.